Okay, so today I'm going to continue to talk about this categorical perspective on type refinement systems as modeled as functors from a category D to a category T, where this category, the objects, we think of them as types a la Curie, and the morphisms are we think of them as typing derivations. And then from D to a category T, where we think of the objects as types a la Church, and we think of the morphisms as terms. And I put everything in quotes because I mean this is kind of a definition. So we're studying type refinement systems as functors. And remember, maybe I'll just recall the definitions, the basic definitions from last time, that we say that R refines A if it's mapped by the functor to A. And we call this, this is a typing judgment where R refines A. Implicitly, R refines A. F is a morphism from A to B in T, and S refines B. So this is a type. This is refinement. These are typing judgments. It's also we talk about subtyping, which I'll write today like this, which is just a special case of this, where here I'm writing A for the identity on A. And then finally, typing derivations. A derivation of a judgment like this is just going to be defined as a morphism from R to S in D, which is mapped by the functor to F. Okay. So we can think of these two categories like this again. We have types a la Curie, typing derivations, types a la Church, and terms. But again, this is an abstract definition that we can instantiate in different ways. And so we can instantiate it in, to study systems which are more syntactically presented, like I showed you last time the example of Hoare logic, where our category here was just a one-object category where the morphisms corresponded to commands. And then the category here were different logical predicates, and the morphisms correspond to derivations of Hoare triples, or a verification that a verification of a Hoare triple that the command C start beginning in a state P will end in a state Q. We see that as we have a category D here where there's an object P and object Q. These are two predicates, and there's a morphism alpha from there. And then in our category below, which is a one-object category, we have this morphism C. And then the functor, it maps everything. It maps every object. I'll call this star. It maps every object P and Q to star, because we just have predicates on the state, on one state, and it maps alpha to C. So P and Q get mapped to star, and alpha gets mapped to C. So here I would write, in this notation, I would write that alpha is a derivation of this judgment. It's a proof of that C will take any state satisfying P to a state satisfying Q. So, okay, so we have these little examples like this. I also talked about another example, which I think you've seen before, but I called it subset over set, where set is the category whose objects are sets and the morphisms are functions. Subset is the category where the objects are pairs of a set equipped with a subset of that set. And then the morphisms a morphism from A to B is a function f from A to B such that for all A, if A is in R, then f of A is in S. Okay. So I just want to give you now a couple of other, so this is a more semantic, you can think of it, a more semantically defined type refinement system. So, maybe we're used to thinking about typing derivations and terms syntactically as maybe as some sort of syntax, maybe some sort of abstract syntax trees, and derivations are inductively defined. I'm deliberately not taking that point of view and defining a type refinement system more abstractly as just a functor, so that this is also a type refinement system in this more general sense, but it's a kind of a semantically defined type refinement system. Also, these categories in the terminology of category theory, these are large categories rather than small categories in these size issues. But there's a couple of examples other than this one, which is pretty familiar, the idea of modeling types of sets and refinements of subsets of those sets. There's other examples which are actually generalizations of this example, which are also interesting and useful to have in mind. So I'll give you two examples and then maybe another third one. Okay, so one example, a generalization of this one, where we replace set by the category of partially ordered sets and order-preserving functions. Okay, so this category is poset, and then we replace subset by, I'll call it downset. So this is going to be, the objects are going to be pairs A of a partially ordered set, R, which is a subset of A, but then also we have the condition that R is downwards closed. Meaning that if A is below A prime and A prime is in R, then A is in R. So that's the definition of the refinement system of the objects, and the morphisms are the same as here. So again, a morphism from A R to B S is now it's going to be an order preserving function from A to B, such that the same condition. And I forgot to actually define what is the functor from here to here and from here to here, but it's the obvious thing. So this is just the functor. I'm not even giving it a name, but it's the functor which sends the pair AR to A. So it's the first projection. So this is one way of generalizing this model. But there's another one which is quite interesting, where we replace set by a category rel. So what this is, what I mean by rel is the objects are sets, and the morphisms are relations. So I'll write M for the morphisms in rel, and M is a relation from A to B. So just a warning, I think that in Patricia Johan's talk, she talked a lot about relations by fibration, and you wrote rel for a certain category. It's a different category than what I'm talking about here. But here the objects are sets, the morphisms are relations. The composition in this category is relational composition. So M compose N is the relational composition of M and N, which means that it relates A to C if there exists a B such that A is related to B by M, and C is related B is related to C by N. And then so this is relational composition, and then the identity is given by the equality relation. So this forms a category called rel. Some people call it rel. I like to call it rel. But now there's also, we're going to form a refinement system over it, and I'll write this rel dot, and I'll explain that in a second. But it's basically defined in the same way as the other cases. So morphisms. So the objects of this category again are going to be sets now and subsets of those sets. But now the morphisms a morphism from AR to BS is going to be a relation from A to B. Let me just introduce a bit of a notation. I'm going to write the morphisms in A like this. I'm going to put a little, the morphisms in rel, I'm going to write them like this just to indicate that this is a relation. So M is a relation from A to B, and and for all A and B now, if R of A and A is related to B by M, then S of B. I should use the notation I'm using before. So if A is in R and A is related by M to B, then B is in S. So this is, you can see it as a relational generalization of this. This notation rel bullet is just because you can see these objects as actually as morphisms morphisms in a subset of A is the same thing as a relation from 1 into A. So the objects of this are like a an object of you can see this as a pointed version of rel. So the objects are an object equipped with a global element, morphism from 1 to A. But that's just a notation. So okay, let me erase this. Here, I generalize this by replacing sets by posets. Here, by replacing functions by relations. We can kind of combine them, and we can consider ordered relations. So here, the objects are posets, partially ordered sets, and a morphism from A to B is going to be a downwards closed subset of so it's a relation. You can think of it as an ordered relation from A to B, and formally it's a downwards closed subset of ordered pairs of A and B, but where we swap the ordering on A. And then the refinement system is going to be defined in the same way like this case. And let me just tell you one and a half more generalizations, and then move on a little bit. So before getting there, so one property of a type refinement system, one property that we might talk about is, well, suppose we have a typing judgment. Is there more than one way to derive the typing judgment? So can you have a derivation alpha 1 and a derivation alpha 2 of the same typing judgment, two different ones? Or do they have to be equal? And in some of the examples I gave you, I think last time, I mean, there were both cases. There were some, in some cases, there's only one derivation of, there's only at most one derivation of the same typing judgment. So let me just, define or convention that if you have this property that this and this implies alpha 1 is equal to alpha 2, so there's at most one derivation of the same typing judgment, then we'll call that a proof irrelevant refinement system. So it was implicit in what I was doing last time. So these are categories. D and T are categories, and they have morphisms, and both of them have morphisms, and there's some equations which are the axioms of a category. Like, for example, composition is associative, and composing with the identity is the identity. Those are axioms, equations which have to hold on morphisms, and we assume those equations. That's part of the formal definition, these being categories. In the case of a proof irrelevant refinement system, it's easy to check those equations because we always have at most one derivation of the same typing judgment. And all the examples that I gave here, these are all proof irrelevant refinement systems. So another way of thinking about that is if I have some if I have some typing judgment, I just ask, is it valid or not? Is there a derivation of this or not? And so that's a point of view that maybe is more familiar for we're thinking about like Hoare logic. In Hoare logic, usually we think about it in a proof-irrelevant sense. We just care whether the command takes a state satisfying P to a state satisfying Q. But in other situations, we might actually care about the proofs of these facts. So I want to show you one more semantic example, one more semantic refinement system, which is proof relevant. And I'm just going to mention this. I'm going to mention this example, maybe for the people who have a bit more background. Otherwise, it's not so important. But just to keep in mind that it's a proof relevant example. So here I'm going to replace set by cat. Cat is the category where the objects are categories, and the morphisms are functors. And now, above that category, I'm going to take a category where the objects are pairs of a category. And okay, instead of saying a subset of that category, we're going to say that the categorical version of a subset is a presheaf. So it's a functor from A up to set. So really, this is a generalization. You can see this as a generalization of this example of where we have posetsets and downward closed subsets of those posetsets. A postset is a special kind of category. Rather than having downwards closed sets, we're going to have presheafs. A presheaf, that's just the name for a functor from A up to set. And then the morphisms, a morphism from AR to BS is going to be now a functor from A to B, together with a natural transformation from R into S composed with F. So if you draw it diagrammatically, we have R, S, F, and then the derivation of this judgment is going to be a natural transformation from R to F post-composed with S. So if you're not very familiar with working with these kinds of natural transformations, I think that maybe it's not so important. But just what I want to emphasize in this example, where again the refinement system itself is just a forgetful map as usual, it's a proof-relevant example. It's a proof-relevant refinement system because we can have more than one derivation of the same typing judgment. Any natural transformation gives us a derivation. Okay. Yes?
Why is it A off instead of A?
It could be A as well. So it's just by convention. Like here for post set, I chose to have downwards closed sets. It could be upwards closed sets. But, yeah. So, okay. So I started to talk, at the end, last time in the questions, I mentioned intersection types I mean, we talked a couple of days ago a lot about intersection types, and we can talk about them basically in a very similar way. We can talk about them in this categorical setting. We can talk about a refinement system having intersection types or having union types. So maybe I will just show you how to define them formally. So intersections. I'll spell out the definition, and then you can work it out for yourself for what's the definition for unions, or you can look in the notes. But an intersection of two refinements so if we have R1 that refines A, R2 refines A, then an intersection is going to be another refinement of A, which comes with a pair of elimination rules. So there's the first projection. There's also the second projection. Maybe I'll call this I instead of, okay. So there's two elimination rules, and there's an introduction rule. This looks pretty familiar, pretty similar to the typing rules that we talked about before for simply typed lambda calculus extended with intersections. But now we're just going to do one more thing, which is we're going to add equations on typing derivations, to get the categorical version of intersection types. So the equations we want are just, so if we have, there's two equations. If we have a derivation beta 1 of this guy and this one, and now we apply this rule, the introduction rule. And now we compose it with one of these two eliminations. So I'll just write again I, it could be R1 or R2. And we compose these to get a derivation of the judgment f has type S0 Ri. Then this should be equal to one of the original derivations. This should be equal to beta I. I'm using the Greek letter beta because this is kind of analogous to a beta reduction. This reduction of an introduction rule composed with an elimination rule. And then we also have a corresponding eta equation, which is that any derivation, if we have a derivation of a derivation, and I'm going to call it eta, of this judgment, we can expand it into one that ends in the introduction rule. We're here now. We compose with the elimination rules. So this is our definition of intersections. for a general refinement system seen as a functor. And this is you can kind of, these rules look pretty similar to the introduction elimination rules I gave you before for simply type lambda calculus. There's these additional equations which are a bit less familiar, though you can think again in the proof irrelevant case, if we're in a working somewhere where there's at most one typing derivation of a given judgment, then the equations become trivial. We know that these are two derivations of the same judgment, so they have to be equal. So we can discharge that assumption. So these are, defining intersection types. You can give a dual definition of union types. And, well, do these refinement systems have intersection types? They do. And the intersection in so in subset, it's just, well, the intersection is just intersection. So you take the intersection of subsets. And the same in the other proof irrelevant examples. But I just wanted to show you. So in the other example of pre-sheaves over cat, here if you have R1, which is R1 and R2 are both pre-sheaves on A, or set-valued functors on A, then their intersection is going to be defined as the pointwise product okay, and there's a similarly union is going to be defined as the pointwise coproduct or disjoint union. Okay. So let's see. One more thing, jumping back a bit to this example. Let me see. So, okay. So I want to, I gave you these examples. I just want to now give you some more structure, to describe some more structure on this example. So this is also a bifibration, like subset. For subset, we saw that push f of AR is the image. So it's going to be B. It's going to be a subset of B, and it's just the image of R. Pull f of BS is going to be a subset of A, and it's just the inverse image. So that's one model of push forward and pullback. In this refinement system, it's just a little bit different. So the pullback is still going to be the same, defined the same way. But just, so let me restate this. So, right. So just an equivalent way, remember that an equivalent way of defining the image, right? So image of R is f of a, the set of f of a, where a is in R. The inverse image is the set of a such that f of a is in S. There's the symmetric definition. So here, the pullback is going to be this thing, which is, again, the same. It's the set of A such that f of A is in S. But now the push forward is a little bit different. So it's, again, it's a subset of B. But now, instead of taking the image, it's going to be the set of B such that there exists an A such that B is below f of A. There exists an A such that, first of all, A is in R, and B is below f of A. So you can see this as we're taking really the downwards closure of the image of R under F. And the difference between these really, if you think about it, the difference between these definitions is because if you have a downwards closed subset and you take the inverse image of a downwards closed subset along a monotone map, is going to be automatically downwards closed. But taking the image doesn't have this property. So if I take the image of a downwards closed subset, it's not necessarily downwards closed, so I have to close it. So that's the definition of the bifibrational structure of this downwards closed subsets over partially ordered sets. The bifibrational structure of this one turns out to be also even more interesting. So I'll give it to you. So if we have the push forward of a subset R along a relation is going to be defined. It's going to be defined like this. So it's a set of B such that there exists an A is in R, and A is related by M to B. And the pullback is going to be the set of A such that for all B, if A is related by M to B, then B is in S. So the push forward and the pullback in this refinement system, the relational refinement system, they correspond to existential quantification and universal quantification along a relation. So that's interesting because in this example, really, you have the two quantifiers, existential quantifier and the universal quantifier correspond to the push forward and the pullback in this refinement system. And we have a symmetry between these two, whereas in the subset and set, image and inverse image are both kind of equally easy to compute. In this example, the downset over poset, the push forwards, you introduce an existential quantifier. The pullback, though, is still easy to compute. And in the relational version, both the push forward and the pullback correspond to existential universal quantification. Okay. So let me just a few more facts about the interaction of push forward and pullback with intersection and union, or union and intersection. So you can show this. So the push forward of a union, R1 union R2 along F is equivalent to a union of push forwards. And when I write this, remember what I mean is that these are isomorphic as refinements. You can construct, from the definitions, you can construct a pair of subtyping derivations in both directions, which compose to the identity. There is similarly, the dual of this, the pullback of G, the pullback along G of R of S1 intersect S2 is the pullback of G S1 intersect pullback of G S2. So you have this and this. So you can try to prove these that these are equivalent. But now there's also you might consider this is push forward distributes over union, pullback distributes over intersection. What about push forward with intersection? So we have this. We have that if the push forward of an intersection along F is a subtype of the intersection of the push forward R1, push forward FR2. But the reverse doesn't hold. They're not equivalent. And it's an exercise to find a counterexample to this. So you can't prove this. So you can't. These two equations, we can prove them from the axioms. From the definition of push forward and union, pullback, and intersection, we can prove that these are equivalent. Here we can only prove it in one direction. We can't prove the reverse direction. But it's you can find an actual counterexample, give a refinement system, and instantiate F R1 and R2 such that you have an actual counterexample to the reverse direction. So you can think about that, and there's similarly for pullbacks. So in general, the pullbacks don't commute with the union, or they don't distribute over the union. So that's also in the exercises to find a counterexample to the reverse direction. So if you have the pullback of R1 union R2 along G, in general you don't have that's included in this union. And that's a trickier exercise, but if you want to think about it, try to find a counterexample to the reverse direction. Okay. So, do people have questions about what I've said so far? So the one yeah. So for pre-sheaves over cat, it's also a bifibration. And yeah, I think I can explain it to you offline. And there's also a relational version of that one, like we replaced subset over set by rel, bullet over rel. There's also a relational version of the pre-sheaf example. Okay, so okay. So here we have intersections, unions, push forward and pull back. We get some interactions, but it turns out what gets really interesting is when we have the additional structure of. Okay, maybe let me back up. So we began, on day one we talked about simply type lambda calculus, and the first refinement system that we talked about was it had these function type refinements. This was one of the first rules that we wrote down. If we have a refinement R of A and we have a refinement S of B, then we can form the function type R or S is a refinement of A or B. And right, at the end of yesterday, in the questions, I also mentioned something like this. So we might imagine having being able to refine product types. If we have, so these have the same premises of R is a refinement of A, S is a refinement of B. We can form refinement of the product type. So a way of talking about this situation, this kind of situation in general, is that what's going on is we talked about type refinement systems as functors between arbitrary categories, but we might ask that, well, actually, these two categories, they have some extra structure. So, T has some structure, foo, and so, okay, maybe we'll call it a foo category, and D is also a foo category. And then the functor R, it's not just a functor, but it preserves the foo structure. Okay, so one example for foo is that gives you this is we take D and T to be both Cartesian closed categories. And we ask that the functor R strictly preserves the Cartesian closed structure. And you can see that here in these rules. What is that saying? If we read these rules, these refinement rules, the refinement rules in terms of the abstract definition of refinement that we have here, what is this rule saying? So first of all, it's saying that R of R is equal to A and R of S is equal to B. Okay, so now we look at R of R times S, and well, if the functor R preserves Cartesian products, that means that R of R times S should be R of R times R of S, and then which is equal to A times B. And the same thing works here, so the functor applied to R or S is equal to the functor applied to R arrow the functor applied to S, which is equal to A arrow B. So these refinement rules, you can see them really what they're expressing is the fact that the functor is a homomorphism in this sense. It strictly preserves the structure that we're interested in. So these examples are both Cartesian closed refinement systems in this sense. So here, the product structure is the product structure is just going to be the Cartesian product of sets, and we can write that like this. So if we have A and we have B, we form their Cartesian product A times B, and then this is going to consist of the set of pairs AB, where A is in R and B is in S. And then the function refinements, or the closed structure for this is going to be now a subset of the subset of the function space, the set of functions from A to B, together with the set, so the subset of functions from A to B, which map everything in R to something in S. So this kind of internalizes the definition of the morphisms in this category. And the same thing, basically the same thing works, the same definition works here for partially ordered sets and downward closed sets. Also the example of the pre-sheaf refinement system also it's also Cartesian closed, where now in the base category, in cat, you're taking the Cartesian closed structure in your types is forming product categories and functor categories, and then the Cartesian closed structure on pre-sheaves is taking, let me write out the definition. Just to have it. So if we have two pre-sheaves, A op are a set and B op are a set, we're going to form R times S is going to be a pre-sheaf over the product category. And, well, it's just defined pointwise. So for any pair AB, it's RA times SB. And then R arrow S is now going to be defined on the functor category. It's a pre-sheaf on a functor category. And it sends any functor F to the set of natural transformations from R into S composed F op. Now, okay, let me see how much time. Okay, we have time. So the example of rel, rel bullets over rel, it's actually a little bit different because it's not Cartesian closed, but it is monoidal closed. So I think you didn't talk about monoidal closed categories. You didn't get to that, but monoidal categories, you can see there's a more general version of Cartesian categories with lots of applications. It's tied to linear logic. And so instead of having the categorical product, we have a tensor product, A tensor B, and So we have a product on a monoidal category has a product operation, and it has to be associative and with a unit. It has a unit, and these all hold up to some good isomorphism. And then there's different versions of monoidal categories. So there's symmetric monoidal categories where you have some isomorphism. There's different versions of. So there's a symmetric monoidal category where you have you can swap A and B, like an exchange axiom, and this has to satisfy some good equations. And then Cartesian categories, you can see them as monoidal categories where what you have is you have, for every A, you have a duplication operation. You can take A into A tensor A, and you have a erasure operation that will throw away A, and they satisfy some equations. So then you can talk about monoidal closed categories, a monoidal category being closed. And it's the same definition as for Cartesian closed, except that now instead of being Cartesian, we have a general monoidal structure. And it, you can define it. One way to define it is just that you have these adjunctions. So the set of maps from A tensor B into C is naturally isomorphic to the set of maps from B into A arrow C, where now I'm using the notation of linear logic. Yeah. Right, so here this is a functor from, I was writing, it's a functor from 1 into C, so it's the same thing as an object of C. So you have this in a, in general, if a monoidal category is not symmetric, you might have left and right versions of this. So you might also have a right implication. So this, you can curry on the left or curry on the right. And in a symmetric monoidal category, these are equivalent. But so okay, so so a monoidal closed refinement system, or a symmetric monoidal closed refinement system. Let's stick with symmetric monoidal closed refinement system. Is just you have a pair of symmetric monoidal closed refinement symmetric monoidal closed categories, and you have a functor which strictly preserves the symmetric monoidal closed structure. And so that's going to give you then the same. It's going to give you a way of refining the monoidal closed symmetric monoidal closed structure below by the symmetric monoidal closed structure above. And so I'll just write the same thing, but now I'll write it like with a tensor and a lolly. And so this other example of rel rel bullet over rel is a a symmetric monoidal closed refinement system. And okay, so that's in the notes, how to show that it's a symmetric monoidal closed refinement system. I think I'm going to move on, and then maybe if we have time, I'll come back and to describe that for you. But so I think I want to go now to some examples. Okay, so let's go back to what we did in the beginning. We were looking at simply typed lambda calculus, and starting from simply typed lambda calculus over a single base type, and then refining it with a collection of atoms and some subtyping relationship between the atoms, which we then lifted to a subtyping relation between general types, higher order types, and we had this type system. So a way of looking at that abstractly is lambda arrow, the simply typed lambda calculus on one base type, we can at least approximate that by the free Cartesian closed category on one element, with the free Cartesian closed category over the category 1. And now, suppose we have another category P. So this is what we started from a set of atoms P with some preorder. So now instead of asking for preorder, we're going to say, okay, it's in general, it could be a preorder, it could be a category. And you can construct the free Cartesian closed category on P now. And then there's a functor, a forgetful functor from this category to this category, which is just extending the functor there's always the functor from any category P to 1, which collapses everything, sends every object to, all it can do is send an object to the single object of this, and the single morphism, every morphism is sent to the identity morphism on this. So we have this functor, then we can lift it to a functor from the free Cartesian closed category over P to the free Cartesian closed category over 1. And that's, you can see that as really, that's the refinement system that we studied at the beginning, the simple one where all you had was this rule. And you had the corresponding typing rules, and you had subtyping relation. You can model it inside this refinement system. And what's useful about that? Why is that useful view? So one thing you can get out of that is, for example, right. So say we want to give a set theoretic semantics to simply type lambda calculus, and now we want to give a set theoretic semantics to our type refinement system. So this was in the notes, but I didn't have time to go over it before in the class. But we're going to interpret. Okay, let me write it like this. So we're going to interpret iota by some set D. Let's say we want to interpret the atomic type iota by some set D, and then we want to interpret the atoms, different atoms P, Q, as different subsets of D. So that's a way of capturing the intuitive semantics that we had of this the type refinement system, that we could model simply type lambda terms as functions between sets, and then model refinements as subsets of those sets, and then the typing derivations were establishing certain inclusions. So So suppose we begin with our category, which is representing the atomic refinements, and we view it as a refinement system, a trivial refinement system over 1. Remember, any category defines a trivial refinement system over 1. And now we map it into subset over set. So what does this mean? This is a morphism of refinement systems. The morphism between refinement systems is just going to be a square like this that commutes. A commutative square like this. A functor from 1 to set it's just picking an object of set. And now this is an interpretation of atoms as subsets. But the fact that this square commutes, it means that we're interpreting every atom as a subset of D. So that's what the square is saying, that we have D, and then every atom is going to get interpreted as a subset of D. But now, if we have this, the fact that these are 3 Cartesian closed categories, it's going to give us automatically that we can lift this, we can extend this to a morphism of refinement systems from here into subset over set. And this is the semantic interpretation. So we're building a model of our type refinement system in subset over set, where we're modeling the category below, where the objects are simple types with 1 atomic base type. We're modeling them as sets, and the terms as functions between sets. And then we're modeling our refinements as subsets of the, so we're modeling them as subsets, and as the typing derivations are stating fact about how the functions that we defined here, the properties, how they map certain subsets to other subsets. I'm not saying that very clearly, but I think it's not worth spelling out more because it's in the notes, and I want to get to some more interesting examples. Okay, so yeah, so let me get to this example. So here, maybe just to say one word about this. In this case, we just have the Cartesian closed structure, and that's it. We don't have any pullbacks or push forwards. Like last time, mostly I mentioned about just the structure of push forwards, pullbacks, intersection unions. What is really interesting is when you combine the two. So when you combine our refinement system, which is Cartesian closed or monoidal closed, and more generally monoidal closed or symmetric monoidal closed, and which is at the same time, it's a bifibration, or at least it has some pullbacks and push forwards, and maybe it also has intersections and unions. But really, it's the interaction of these, the tensor, the implication, and the push, and the pull, which get to interesting structure. And another way of looking at that, I mentioned that in this particular refinement system, the push forward and the pullback were corresponded to existential and universal quantification. So it's combining the tensor implication with the existential and universal quantification where you can start to model interesting situations. So I'm going to talk about now back. We talked about Hoare logics a few times, about how you can model Hoare logic as a refinement system. You can try to extend this to separation logic, and how does that work? So for Hoare logic, we had this and this, where T was a one-object category. And a one-object category is essentially a monoid, and it corresponds to the monoid of commands. Commands closed under sequential composition. For separation logic, what we're going to do is we're going to replace the one-object category. Instead, we're going to say that we have now a symmetric monoidal closed category which contains a monoid object. So how does that work? What is a monoid? A monoid object you can define in any monoidal category. And it's going to be some object W together with a multiplication operation from W tensor W to W, and a unit for the tensor, and these satisfy the axioms of a monoid, so it's associative and unital. So suppose we have something like this. Now, the intuition for separation logic, these are supposed to represent, W represents the collection of heaps, and the monoid operation corresponds to the operation of merging heaps, and then this is the empty heap. So in separation logic, we have these connectives, the star separating conjunction and the magic wand, so-called magic wand. And they actually, if we're viewing predicates as refinements, so we're viewing a predicate on the heap is a refinement of W. Maybe I will change W to be H. Okay, so this is the heaps. Okay, so P is a predicate on the H. We see that, we model that as P is a refinement of H. And here we have operations for forming new predicates on the heap. So P star Q is again a refinement of H. It's a predicate on heaps. And P magic wand Q is again a predicate on the heaps. But so the question is, what are these connectives? Well, I showed you before we had a general, in a symmetric monoidal closed refinement system, we have these operations of tensor and implication, but tensor and implication, they look a bit like the separating conjunction and magic wand, but they have a different shape. So here we're asking that R refines A, S refines B, then R tensor S refines A tensor B. So these are different, these could potentially be different, and then we take their tensor, and similarly for the implication, R implies S is a refinement of A or B. But so this is the trick, is that we can decompose these connectives in terms of these connectives combined with push forward and pull back. So we're going to define P star Q as being, well, we take P tensor Q, and then we push it forward along M. So here, let's see how that works. Or just to check that this type checks. So we have P as a refinement of H, Q is a refinement of H, P tensor Q is a refinement of H tensor H, and then M is an operation from H tensor H to H, and when we take the push forward, we get a refinement of H. Okay, so it has the right type, right refinement. Similarly, for the P magic wand Q, okay, we're going to begin by forming P lolly Q. Let's start to construct it here. Okay, so we have P refining H, Q refining H, P lolly Q refines H lolly H. Okay, so we have P refining H, Q refining H. Then P implies Q is a refinement of H lolly H, so it's a refinement of heap transformers rather than heaps. But we want a refinement of heaps. So somehow we need some operation from heaps into heap transformers. So does anyone have an idea about what we could take for this operation? The identity morphism? Well, there isn't, the identities you have just between the same objects of the same, every object has an identity morphism to itself. So there isn't, we don't have an identity, but is there another way that we can construct a morphism like this? Sorry?
I think maybe that you can carry using another structure.
So which map should I curry? Would you like to curry? Sorry? M. So we have M, which is from H tensor H to H, and when we curry it, we get a map from H to H lolly H. So we have this, and now we pull back along this map. And we have a refinement of H. And so this is our definition. Okay, so we've defined star and magic wand, and we can do the same thing for the unit. So amp we can define as now the push forward along E of the unit refinement. So you can see these as abstract definitions of a separating conjunction magic wand, and so like we can prove things. I should finish. Yeah. So we can prove things abstractly about these definitions. Like for example, we can show that there's an adjunction P star Q is a subtype of R at H if and only if Q is a subtype of P star R. We can prove this abstractly, but we can also instantiate these definitions in particular models like subset or rel. So what happens if we instantiate it in subset? So we assume that we have a function pairing operation on heaps, and then if you work out what it says, I'll write it like this. So maybe I should write it like this. H is an element of P star Q if and only if there exists H1, H2, such that H is equal to H1, M of H1, H2, and H1 is in P, and H2 is in Q. So this is one of the the usual definitions of the separating conjunction, semantics of the separating conjunction, but we've decomposed it in terms of two things: in terms of the tensor product, this operation, and in terms of the push forward. So you can see here that this part corresponds to the tensor, the definition of the tensor in the refinement system subset over set, and then this existential quantifier comes from the push forward. And similarly for the magic wand, we can, the definition that we get is that for any H prime, if H prime is in P, then M of H prime is in Q. And here you can see this. We're decomposing it in terms of the definition, the general definition of the in fact the Cartesian closed structure in this case of subset over set, together with here is now the pullback. We're pulling back along the Kering map. That's how we get this thing here. So this is modeling it in subset over set. We can also do it in rel over rel bullet over rel, and that lets us give the semantics, the relational semantics, where what a monoid object in set is just a monoid, but a monoid object in rel is more general. So like partial commutative monoid, you could model as a monoid in rel. Let me just give you two more examples. Maybe I should do one more example. Let me. Okay. One quick example. suppose we have some plugging operation, some binary operation, but it takes two things, an A and a B, returns a C. These are arbitrary types. But now we fixed some refinement of C, and I'm calling it obs. It's an observation on C. Now for any, if we have a refinement R of A, we can construct R ops, which is a refinement of A lolly C. And now we can pull back. We can do the same trick that we did here. So we can pull back along the currying of plug, the left currying. Which way is it? So we have from plug we get operations B arrow A lolly C. That's a left currying of plug. And we also have right currying. And this gives us a refinement of B. So this thing, I'm going to call it R perp or R dual. So we can turn a refinement of A into a refinement of B. But then we can also go the other way around. So given if S is a refinement of B, then we can form the pullback along the right currying, a plug of S right implies ops, and this whole thing is a refinement of A. And so this is a you can see this is connected to biorthogonality. So now what we have is for any R and S, which refine A and B, when you plug them, that goes to this type obs, just in case by currying, just in case S goes by currying of the plug to R lolly obs, and just in case S is a subtype at B of R perp. And the same thing, we can show that this is if and only if R is a subtype of S perp. So we have a contravariant adjunction between on the one hand, the refinements of A and the refinements of B. So this is a pattern that we can instantiate with different plugging operations and different observations. And okay, maybe I'm gonna end now, and just by telling you one more example. So, you know, we've talked about in the beginning. We talked about refining a simply typed lambda calculus. It was easy to see the structure, the refinement structure there, because everything at the beginning the refinements just mirrored completely the structure of types. Then we added intersections, but in kind of systems that you see in the wild, what I would consider a type refinement system, where you're constructing a type system over a typed language. But you know, Scheme is also a typed language in some sense, and Python, because they're dynamically typed. But so a way to approach modeling those situations is to say, well, actually what you have is, below you have a recursive type. And so for lambda calculus, for pure lambda calculus, there's the idea that you can model it by a universal type. So this is Dana Scott's idea that inside a Cartesian closed category, you can have an object he called a reflexive object. And it's a pair of maps. So app for application and lambda, which satisfy this equation for the beta axiom. This is a reflexive object in a Cartesian closed category. There's different ways to generalize this, maybe to relax the requirement that you have an equation. This is the beta law. And you might also have some sort of eta law. But the basic idea is you have a type U, and you have a pair of operations corresponding to application and lambda. And now you can think about, well, we can define different refinement types as refinements of U. We can refine the reflexive object. And so we can define two operations. So okay, we can form R arrow S, and then we can pull it back along application, and that will give us a refinement of U. But we could push forward along lambda, and that will give us a refinement of U. And in general, these things might be a little bit different, but okay. But you can see this is the kind of ideas that you might use to give a kind of untyped realizability style semantics to lambda, to model that kind of semantics where we're viewing, traditionally viewing types as subsets of collections of untyped terms. We can talk about that in this framework and this kind of style. So if people have more questions, or any questions about anything. Okay, thank you.
On behalf of everyone at OPLSS, I'd like to thank you for your lectures and for really refining our understanding of types and categories.
Thank you all very much.